yeah, it gives a little disclaimer. Because these are recorded and because the book is pretty complete, I'm not actually going to post these notes. I'm just going to toss them away at the end of every lecture. So if you want to take notes, by all means. If you want to just watch and just follow along in the book, that also works just as well. We're going to follow this, this online LibreOffice book fairly closely, so you should be fine in that regard. That book does not have homework assignments in it, so I'll be writing those myself or talking to colleagues to get those homework assignments. But right, so it's 1:11. I hope everybody's day is going all right. First time I've taught an online course, so I guess we'll see how this goes. First of all, you guys know that my name is Sam Blitz. Please don't call me Professor or Dr. Blitz, or even Mr. Blitz makes me feel old because, you know, I guess I am kind of significantly older than you, but like not that much, right? So just call me Sam. I don't think about a point in my life where I need 18 to 20-year-olds calling me Mr. anything, because I still feel, well, I don't know. When you get older, you never feel like you're getting older, so. Right, so the first thing that I should probably let you know is that I haven't figured out when I'm going to do office hours yet. I'll post those with an announcement on Canvas once I get that sorted out. I'm just trying to let the TAs handle their office hours. There are a whole lot of things that are going to be different this quarter just because of the online nature. For example, as many of you guys have already seen in the syllabus, homepage of the Canvas site, the labs are going to be done basically individually. There will be some lab assignments that are posted on the lab website, a link to which is found again in the syllabus, and you'll basically be doing those assignments and submitting them to the, oh, okay, mic just got weird. Am I still covering it? Thanks for the memo. All right. Is everything good? No? Okay. Hold on. I may have a... All right. No, I know I muted. I was talking to some people who wanted to spectate separately. Mic better? Mic quality? Okay, yeah. So admission of guilt here. I had some friends who wanted to watch the lecture, so I was streaming it in Discord as well. Presumably streaming it on 2 services is probably what caused the issue. So I stopped streaming it on Discord. They can watch physics lectures later. Anyway, so where was I? Right, so there's this whole business with labs, which hopefully you can find links to the lab website on the syllabus on Canvas. There will be basically labs to do at home that you're going to do on your own. It's not going to be via Canvas meetings or Zoom meetings rather or anything. It's just, it's almost basically extra homework, but keep in mind that you're not going to have to spend 2.5 hours in a room doing a lab. You'll just spend 2.5 hours in your home doing homework. So, you know, online school makes things harder because, you know, there's more homework involved, but it is the way that we have to do. Also, this whole business with discussion, typically I would just make discussion mandatory and then I take attendance, and then that would be all of your discussion grade. But because, again, discussion is not mandatory here, if only because some people aren't even in the United States anymore and they can't make it to the lecture, or sorry, they can't make it to the discussion because, you know, it'd be 2 a.m. for them or whatever. Instead, I'm just giving you guys discussion worksheets that your discussion TA will work with you on. So feel free, there will be Zoom meetings to attend with your discussion TA in you know, groups of 25 to 30 people or so. And, you know, he'll divvy it up and make it so you guys are working in smaller groups and all that business, and it'll just be normal. But at the end of the discussion meeting, hopefully you will have been taking notes or writing down your answers to various problems in the discussion handout. and then you just submit that. Now, that's not going to be graded for correctness or anything. It's going to be graded for basically, did you do everything? And if you did, you'll get full points. If you didn't, if you did most of it, you'll get 75% of the points. If you didn't do it or you didn't submit it, you'll get 0 points. So that's basically the way that we're going to be taking attendance, and that will account for this whole high pass, low pass, mid pass business, basically how many points you're getting. So if you don't attend discussion, the discussion handouts will still be available to you online in the form of a PDF. You can find it on Gradescope or on Canvas, but you'll have less help. You won't be able to work with your classmates on it, things like that. So if you can make it, attend the discussions, because the discussion TA will be able to help you out. But if not, it won't kill you. Just got to hand in the assignment. Yeah, so that's a good question. So it is often the case that the TAs will not complete that you won't have time in the discussion, the allotted 1 hour or so, to complete the discussion handouts. I'm giving the TA a whole lot of leeway to as to what quantity of the discussion handouts he wants to be rating, because he's rating them, he's marking them for completeness. So if he thinks that there's too much on the discussion handout, it's completely within his power to be like, yeah, this is too much. As a class, we're only going to do the first 2 questions or something. And then he'll send out an announcement, and he'll say, hey, we're only doing these 2 parts. Feel free to not do the other parts if you want, and you'll still get full credit. But in most cases, the discussion handouts are fairly doable. And if you don't, like, some groups might not complete it just because, some groups might be a little slower than others. In that case, it might be an extra 15 or 20 minutes to do on your own, in which case may as well do it, or I guess you could take a little bit of a hit. So everything that you're handing in, will be turned in on Gradescope. Hopefully everybody sees that little link on the left side of their Canvas home webpage. The reason it's not being handed in directly on Canvas is just because the Canvas grader's kind of difficult and bad to use. Hold on. Yeah, so the labs are weird. Typically, the lab materials would be provided for you, in the room that you complete the lab. But honestly, I'm not sure. So the way the 9 series typically works with regards to labs is that there's somebody who's in charge of the labs for all the 9 series courses, that like 9A, 9B, 9C. And that's Tom Wiedemann. He's always in charge of the labs. And so he's in charge of them this quarter as well, just as before. And so I don't really know what goes on in the labs, what's required for the labs. So unfortunately, I can't really help you out there. I can write down his email, and you can, well, maybe that's not the appropriate thing to do. What I would do is, yeah, I don't want you to flood his email with questions. Today's lab is not due till next week. So what I can do is I can send Tom an email tomorrow, or not tomorrow, later today after this lecture, and I'll ask him what materials you'll need, because I just don't know these things. That's his playing field, as it were. Unfortunately, we will have to hold off on answering that. Like I said earlier, the labs are not recorded. They're basically done at home, and they're done by yourselves. Presumably, you won't need any. I can't imagine they would expect you to go out and buy things, especially with the lockdown that everybody's in. But I can't say for certain. The lab times, though, don't matter at all. You're just doing it on your own time. Right. So also, on a different note, there's homework. Homework will be posted every week on Monday afternoon-ish, maybe Tuesday afternoon if I'm feeling lazy. Depends on how long it takes to write, really. But homeworks will be posted, and then they'll be due the following week. And so they'll be posted on Canvas and Gradescope. They will be due again on Gradescope the following week. So typically, typically they'll go out at around Monday, maybe at 3 or 4 p.m. And then they will be due Monday at noon the next week. They will cover material from the Monday, Wednesday, and Friday lectures. And so if you block your time well, then you should be able to do, about a third of the homework on Monday and Tuesday, another third of the homework on Wednesday or Thursday, and another third of the homework over the weekend. Good question. Homework should be submitted as a PDF. You guys all have smartphones, I'm sure. I can't imagine how you would get this far without them. And if you have an iPhone or an Android smartphone, or I guess if you have a Windows phone, I don't even know if those are still a thing, then there are plenty of free apps that you can use to take pictures of documents and have them converted into PDFs. And so it'll do a little bit more post-processing rendering on the photos that you take, makes them more easily readable as PDFs, and like combines them into documents and things like that. It should be easy to deal with. If you want to use LaTeX, by all means, I'm sure your TA would appreciate it. As for the Zoom link, there actually should be, on Canvas, there should be Zoom meetings already scheduled for each discussion every week. Depending on which discussion you're in, you would click on the appropriate things. The labs are going to be due, actually, now that I think about it, I think that the labs are due at the beginning of the week. Let me double check. Again, I didn't set this. This was the instructor that set the lab instructor. It looks like the labs are due every week on Wednesday at 6 p.m. So the textbook, the textbook edition, the hard copy textbook is oh, by the way, to answer the earlier question, you don't have to print anything if you don't want to, because we're not collecting anything as a hard copy. We can't. We're not allowed to. So if you want to just get a PDF, that's fine. If you want to print it out and write on it, that's fine. I'm not going to leave room on the homeworks, so that's fine. Labs, the later labs have not been opened up to you guys yet, because you guys aren't expected to do them yet. So it's not like you'll be able to do everything in advance. The textbook, right? So the textbook is whatever edition, really. I'm not going to be referencing it. It's just another useful reference guide. So if you want to use it, you can. I think the 15th edition is the one that's used by 9B and 9C. But keep in mind, as of like this year or so, we're basically phasing those textbooks out. So don't expect to need to buy it for any future 9 series courses, really. Some instructors might still use it, but I would bet that you won't have to anymore. All right. Does anyone have any other questions about how any of this works before we actually jump into physics? As of right now, we are 13 minutes in. I'm going to run today a little bit longer just so I can answer questions at the end if anybody has any. And I'll usually run lectures about 10 minutes longer than usual anyway, just so people can stick around and ask questions that they don't want to ask in front of everybody else. Anyway, if we are good to go, I'm not seeing any, oh, there's another question. Yeah, so yeah, you'll be turning in a PDF of your notebook or printer paper, whatever you choose to write on, or if you do it on a computer, just convert to a PDF or whatever. Yeah, you'll just be submitting exactly what you would do for normal homework. Just do it on your notebook, and then instead of ripping it out and handing it to someone, rip it out and take a picture of it and send it to Gradescope. Should be pretty easy. Yes, you will need to complete and turn in discussion sheets on Gradescope, not on Canvas. But they are posted on Canvas as well for your viewing pleasure. Right, so I'm going to get started. We'll save more questions for the end because we do have material to actually cover today. So let me start off by saying my name is Sam Blitz. I'm going to do some, move this camera because this is where I write. My name is Sam Blitz. It's spelled B-L-I-T-Z. Call me Sam. Please don't call me anything else. I mean, I guess you could call me Blitz or something, but don't call me Dr. Blitz. I don't have a doctorate. Don't call me Mr. Blitz because that makes me feel old. Don't call me Professor Blitz because I'm not a professor. I'm a grad student. Call me Sam. My email address is shblitz@ucdavis.edu. That email, basically just send me questions about administrative things to that email. If you want to send me physics email or physics questions, just don't, because it's hard to explain things over email. Honestly, because you don't have to go anywhere, just shoot me an email, say, hey, I have this complicated question. Can I meet you with you on Zoom? Or you can come to my office hours, or you can go to a TA's office hours, or whatever. We can schedule something just so it makes it easier to talk about. All right, so now we have to answer the question, what is physics, right? So I'm sure you guys all have this preconceived notion of what physics is, you know, particles and space and black holes. And I mean, that's all true. That is all physics, and it's awesome stuff. And that's what got me into physics. But physics is a lot broader, right? It's the study of the natural world. Really it involves all aspects of the natural world. And the earliest physics was a lot more straightforward. It was a lot more simple. But in particular, this study that we're talking about, it involves the scientific method that hopefully you all learned about in primary school. And in particular, unlike a lot of the other sciences that you'll run into, I mean, other sciences are starting to get that way, but for 400 years or so, physics has been really the only science that uses this language of mathematics to describe the natural world. We take quantitative data rather than qualitative data. That's what makes physics particularly powerful at describing things in nature. So the most fundamental thing that we're going to talk about is motion and interactions. So how do things move, and how do things that are moving or not interact with each other? Yeah, if there's a... Oh, yeah, that's... yeah. Okay, so everybody else can hear me, Ifan, so you can watch the recordings later. He's one of my TAs, so we should be good. Anyway, right, so we're going to be talking about motions and interactions, right? So how do things move? You know, how fast do they move? What direction do they move? And then how do things, when they're moving or not, interact with other things that are moving or not? And keep in mind, this could both be, you know, dropping an apple and seeing how quickly it takes to get to the ground and then stop, or it could be what is the rate that two black holes collide at, right? So, you know, if all we're talking about is motion and interactions, that goes all the way from the most basic things to the most fundamental and esoteric things that you see in physics. It's all just the study of matter and motion. So the question is how do we actually study motion and interactions, right? So the way that physicists and scientists in general have got around to doing so is by developing models. So when I say models, models have a particular meaning, and so when I say model, what I mean is a mental construct that allows us to make predictions about the real world. Now, there's a difference between what a model predicts or what a model says is happening and what is actually happening, right? That is, the models are not necessarily true. And I'm going to put true in air quotes here. Because what I mean by that is that models are just tools for making predictions. I.e., if you were to interpret your model to say it's doing one thing, as long as it outputs as long as it tells you that, you know, your block of matter is moving at such and such a speed, if it agrees with experiment, that's enough. It doesn't matter that the picture that it presents you makes sense, right? Further, models are really only good for what they're designed for, right? So often, some models will have regimes in which they're relevant. What I mean by that is, sometimes the pen dies. What I mean by that is that you might, for example, want to model the sun as a point. If you want to talk about gravity, if you want to talk about orbits of the Earth going around the sun, you would just say, oh, well, the sun's actually a big sphere gas, but let's just imagine it's a point. That would be a model. But if you wanted to study the flow of the fluids on the sun and how the hot gases move and the plasmas fuse together, that model wouldn't be sufficient, right? So we create different models for different situations, and often they're very good for their very specific purpose, but they're not good for other things. An example of such a model would be a frictionless surface, and we're going to run into this a lot. So the frictionless surface is a model that lets us study what happens when you have an object on a surface, and we don't really care about how that object moves around on the surface. Maybe, for example, we want to talk about two blocks colliding. Well, we don't care that they're slowing down because of friction. We just want to see what happens when they collide. We just want to know what happens when two things collide. We don't care about the table being rough or them, or it being smooth. Just an aside, the lectures will be posted pretty quickly after the lecture is actually complete. I'll have to download, re-upload, and then it should be available. Right, so this frictionless surface, it doesn't actually exist, right? There's nothing to say that this model is true because there are no frictionless surfaces. But we use it a lot because if we want to learn about, say, collisions in 2 dimensions, we need those, say, blocks to collide on top of something. We need them to be on something so that it's 2-dimensional. And so we'll just model it as if they're on a frictionless surface. So that's just an example of a model that we will use, but isn't quote unquote true. Right, so throughout this whole course, I'm basically going to be presenting you with well-accepted models that show up in physics all over the place. And then I'm going to teach you how to use those models to make predictions about the real world. Say, maybe I will teach you how to, I don't know, figure out the location that a cannonball will land if you fire it up at some angle, right? That's something that you would need to some sort of model to make predictions about. So there's another thing that shows up in physics pretty frequently. Oh, and my tablet froze. Please let me scroll. Oh, okay, there we go. So it's not enough to just have models, right? We need to actually make predictions. And in order to do, this is just introductory material, certainly. In order to actually make quantitative predictions, rather than just saying the ball will fall there, you need some way to quantify that information. And so here we introduce the idea of measurements and units. So the issue here is that a model might tell you that an apple will fall off a tree, or that the apple will hit the ground after it falls off the tree. What a model won't tell you, or at least you will need to specify what you're using in the model to tell you this, is it won't tell you that the model falls at 10 meters per second squared, or has an acceleration of 10 meters per second squared. So the model is things fall. Great. The measurement / unit is it falls at 10 meters per second squared. So here, this 10 is a measurement, it's a number, and this meters per second squared tells us what those numbers are related to, right? So a unit is an agreed upon reference point to which we can compare measurements. Now, the reason we need these should be fairly obvious at this point, I hope. It's not enough for me to just say, hey, that car is 10 long, right? Like 10 what? Like 10 inches, 10 feet, 10 meters, 10 kilometers. Unless you and someone else can look at the same reference object and say it's 10 of those things long, then any measurement is meaningless. You need some sort of unit in order to tell you exactly what your measurement means. So, for example, I'm 74 inches tall, and we've all agreed, at least in the United States, don't get me started about the United States not switching to metric, but we've all agreed that 1 inch is something that you can go find, it's about that big. You can go find it in the National Institute of Standards and Technology, and they will tell you exactly what 1 inch is referring to. And then if somebody else didn't know how much an inch was, well, they could go to the same place, look at the reference object, and see, oh, that's what he meant. So he is 74 of these tall. Right. So it's not enough to just have our units thrown about left or right. Often we want something called a system of units. So a system of units is basically just a complete set of measurements or a complete set of references that lets you describe various measurements. So for example, your system of units might include a volume, it might include a temperature, it might include time, like duration, It might include brightness. These are all things that we could quantify as long as we have some reference unit to compare to. So if say my reference unit of brightness was, I don't know if you can see this lamp. Where is it? No, that's not the webcam. It should be a lamp back there. Yeah, if my reference unit was one of these lamps is one brightness unit, one blitz brightness, then that would be my reference unit, and that would go in my system of units. And if anybody wanted to measure in that system of units, they'd have to come to my house, look at my lamp, and then compare to that lamp. It's the same with time. A second is defined relative to a second has a given reference. It is, you know, the time that it takes for, well, okay, it is the amount of time that it takes for like 300 trillion oscillations of a particular cesium atom. That's whatever. But the point is a 1 unit of time, a second, is a very specific duration that we refer to. However, so a system of units is just a collection of these. We just call the SI unit system is the collection of reference value or of reference objects or values that we can all collectively refer to describe any measurement: volume, temperature, time, brightness, electric current, a whole bunch of things, energy. So in any system of units, there's something called fundamental units, and these are probably the things you're most familiar with from high school. These are distance, mass, and duration. And so in the SI unit system, which is the one that we're going to be using almost exclusively, distance is in meters, which is which is abbreviated just M. Mass is in kilograms, which is abbreviated kg, and duration is in seconds, which is abbreviated S. There are a few others. We're not going to run into them, but not in this course anyway. There are a few other fundamental units, but for the purposes of this course, any unit we see, whether it be energy or whether it be density or volume or whatever, any unit will just be some combination of these, any measurement. For example, the unit for energy, which is known as a joule, is a kilogram times a meter squared divided by a second squared. And so you can always break up these any measurements into forms of distance, mass, and duration. So just as a warning, I want you guys to pay attention to units whenever you're doing calculations. So often what I run into students doing when they're doing homework is, you know, they'll do some calculation and they'll just work with the numbers instead of carrying around units everywhere. But if you do that, you're very, very liable to get an answer that doesn't make sense. And if you make a mistake, it'll be very easy to catch it if you had carried your units around. So this is using the tools of dimensional analysis that hopefully you guys are all familiar with. And if not, we can talk about it in, say, in office hours if you want to. But right, so that's the whole intro spiel on basically what physics is, how we do measurements, what units are. Now we're going to move into a little bit of a mathematical prelude or mathematical background set of notes. If only because this is a calculus-based course, there's going to be some math that you're going to need. I'm not going to talk about the calculus stuff. Really, we're just going to talk about vectors. Right, so let's start with that. Oh, actually, you know what? Before I start, can I get some... If you want me to slow down, or if you have questions about what I just talked about, this introductory material, go ahead and press the Go Slower button on the chat thing, or under the participants thing. If not, I'll move on, but just that way then I can see if anybody has any additional things. All right, so we have at least one question. So perhaps, oh, nope, okay, hold on. Okay, maybe not. All right, so I guess we'll just continue. So one request for go faster, so I'll do so. Right, so we're going to talk about vectors. So vectors are a requirement for this course. You're not expected to have seen it in math yet, but we do need to talk about it here. A vector is a number paired with a direction. That's all it is. I mean, if you ask a mathematician and you have a master's in mathematics, they'll probably tell you something else, but that's all a physicist cares about, really, when it comes to physics and vectors, right? This number is often denoted as the magnitude of the vector. So when I say, what's the magnitude of that displacement vector, you would give me the number, not the direction. So an example of such a vector, oh, why did it go down? An example of such a vector would be velocity. Velocity, not speed. Velocity is a vector. For an example of this would be 85 miles per hour west. Note that there is a number, a magnitude, and by the way, those numbers will often have units associated with them. And then there's a direction, west. That's all a vector is. So a vector is often represented by an arrow, and the reason is because the length of the arrow tells you the magnitude, and the direction of the arrow, quite obviously, tells you the direction. So we will draw something like this. You'll have your tail of your vector, you'll have the head of your vector. This distance, say for our, this distance is the length, and that represents the magnitude. So, you'd get out your ruler and you'd measure it. And then obviously the direction the arrow points in, that's the direction. Keep in mind that a vector is not actually an arrow, right? It's just a graphical, convenient visualization for for a way for us to talk about and display vectors, but they're not actually arrows. So what would be a good example, or what are good types of vectors? Well, we already mentioned one. One is velocity. Velocity being, or speed being the magnitude of velocity. Another is displacement. So an example of such a vector, such a displacement vector, would be 3 feet northeast. By the way, when we start actually doing calculations, I'll drop the non-SI units, and I'll drop using like this northeast and west notation, well, the more formal way of talking about these things, but this is just for familiarity. Another one is acceleration. Acceleration, in our case, might be 10 meters per second. That's the acceleration that things feel under Earth gravity. And it has a direction. It's down, right? So accelerations, it's not just enough to just provide a number. You need to actually give a direction. Something that I very much want to stress is that you cannot compare vectors with different units, or perhaps different unit types. And when I say that, I mean, sure, you can compare a displacement vector of 1 inch in the west direction with 2 miles in the west direction. Those are reasonable to compare. But you cannot compare a vector that, you cannot compare, say, a velocity, which has a unit type of meters per second, with an acceleration, which has unit type of meters per second squared. It's just nonsensical. It'd be like asking, is 3 meters per second bigger or smaller than 6 inches? It's just a nonsense thing to do. So please try to avoid talking about how a velocity is bigger than an acceleration or something along those lines. It's very easy to screw up, but it's just a general warning. Right, so let me give you some details of vectors. So typically, the location of the tail, and this is not always true, but the location of the tail typically is meaningless. It has no significant, not meaningful, no significant meaning. So meaning that you can just drag vectors along. Like this vector doesn't mean anything more here than it does here, right? It still represents the same direction and the same magnitude. Sometimes, especially in 9C, you'll find that the tail of the vector actually does gain some meaning, and that's just an abuse of notation, basically. But keep in mind that vectors don't really have a location. Their tail can be wherever. Another detail is that vector directions can be reversed by multiplication by -1. And I'll explain what I mean by multiplication in a minute. And I apologize for my handwriting, by the way. It's kind of hard to write on this tablet. Hopefully it's legible. And if not, look at the textbook. Vectors also can be scaled. i.e. their length can be changed by multiplication by a number. Oh, you guys think my handwriting is nice. Excellent. Maybe I just have a hard time following the lines or something. So this number is often called a scalar. A scalar being a quantity that is not a vector, it's just a number in a unit. So in this example, if the scalar is greater than 1, i.e. maybe if it's just 6 or something, then the vector is stretched. If the scalar is less than 1, the vector is shrunk. So what this scalar does is it basically just, like if you multiply by the scalar 2, it takes your vector, keeps it in the same direction, and just doubles its length, right? So there's other things that you can do about vectors. You can add and subtract them. So we know how to add and subtract scalars, i.e. numbers, right? 5 plus 2 is 7. We just know how to do that. 5 meters per second plus 8 meters per second is 13 meters per second. Fine. But vectors have a little bit more than just a value and a unit, right? They have a direction as well. So you can't just say that 5 meters per second west plus 8 meters per second north is 13 meters per second northwest. It doesn't work like that. Instead, you have to somehow combine the direction data with the magnitude data. So the way that we do this, at least with addition, is, at least visually, we place the tail of one vector. Remember, we can move the tails around however we want, to the head of the second vector. And I'll draw what I mean. So if we have a vector like this and we want to add to it, by the way, I'm just doing this visually because we don't have symbolic language for it yet. We want to add to it, say, this vector. Well, that would be, we take the head of one. Let's say we take the tail of this one and add it to the head of that one. So we'd have this vector. Actually, I think I can do this by dragging and dropping. Let's do this the right way. So we take that and we slap this one on top. And our new vector is the vector that goes from the tail of the first one to the head of the second one. So our new vector looks like that. So that's how you do vector addition. Now, keep in mind, it doesn't actually matter what order I added them in. You would get the same triangle when you have all three vectors present, and so you'd get the same final side length and direction. Subtraction can be done very similarly, but the order does matter for subtraction, right? 5 minus 3 is different from 3 minus 5. So in order to do subtraction, let's keep those same vectors. I wish OneNote was less sluggish. Well, how do you subtract two things? All you do is you just add them and put a minus sign in front of one of them, right? So subtracting these two things is the same as adding, as adding negative of that vector, right? I mean, if you just treat vectors as just symbolic things, that should be true. And so we know what putting a negative sign in front of a vector does, right? What it does, oh, come on. Let me scroll, please. There we go. What it does is it reverses the direction of the original vector. So we have that vector, I'm approximating now, and we're adding to it this vector now. And now the order doesn't matter. So this is just the vector that looks like this, with this vector attached to the tail, and now we can get our final vector, which just looks like that. And so this is how you do vector subtraction. You flip one of them, or you flip the one that you're subtracting off, and then add it to the first one. And problem solved, you've done vector subtraction. This is just the negative property of addition, right? It's not particularly difficult. Now, I do have some notation to introduce to you about vectors. So sometimes you'll see a different notation. I'll explain it in a minute. But often you'll see vectors written like this. You'll have a vector A, or a vector B, or a vector C, or a vector X, or a vector R. And you know that these things are vectors because they have these little, like, half arrow things. It's just that. which I think is just a bastardization of this thing, just to indicate, hey, this symbol has a direction as well as a magnitude. So that means this quantity, or that symbol over a quantity, means it's a vector. Now, sometimes instead of seeing that little hat or that little arrow on top of it, sometimes instead you will just see a bolded thing. So it'll just look like this. And that's a very old notation, but that also, okay, well, it auto-deleted it, but that's an old way of writing it. But sometimes you'll see that in textbooks, especially textbooks that are still kind of old. You'll see their vectors just bolded instead of having a little arrow on them. And I have to apologize for that. It's just the way, it's a convention from, 150 years ago. Nothing I can really do about that. The other notation that's important is this notation of a hat. So you'll see maybe a vector I, or a vector v, or a vector n, or a vector capital V, or a vector x, or whatever. When they have that hat, that means they are a unit vector. So that means that their magnitude in whatever system of units is 1, and their direction is whatever the direction of the vector. So if I wrote the vector a hat, what that means is that is the vector a divided by its magnitude. And I'll explain that notation again in a minute. Oh, actually, I'm about to explain that anyway, so I'll just get to that. The last one is you might see this notation where you take a vector and you put bars around it, maybe like this, or like this, or something. Those bars around a vector means just give me the magnitude. So if I had an acceleration vector, say a, and say that's the acceleration 10 meters per second downwards, then the magnitude would just be 10 meters per second squared, or 10 meters per second squared, rather than a magnitude and a direction, right? So this is a good way to extract just the number. And so in particular, you can actually write a unit vector, a, as being the original vector divided by, which is the same as multiplying 1 over, it's over, like 1 divided by 1 times the inverse, divided by its magnitude. The link for the textbook can be found in the syllabus, so check it on Canvas. Right, so what this means is I just take the vector a, and then I multiply it by the quantity that gives it, I multiply it by the inverse of its magnitude. And so what that does is it just scales the magnitude to be precisely 1, right? If you multiply a thing, and that's what scalar multiplication does, it just changes the magnitude. You multiply the magnitude by the inverse of the magnitude, you just get 1, and so it has unit length, magnitude 1, but it still has all of the same directional features of it. Great, okay. So, so far so good. What else can we do with vectors though? Like how do we actually represent them mathematically? Well, it's great that you can manipulate them graphically like we did here, but it's not really enough, and physicists don't do that, right? They have a more symbolic approach to these things. And so these are what are called, the way that we do this is using the language of vector components. So vector components basically tell you, or basically give you a useful way to answer the question of what is the magnitude of a plus b? Right, you have two vectors, a and b. You could either lay them end to end, get out your ruler, and then measure the resulting vector, but maybe you don't have a ruler, right? You could use geometry to find the magnitude of a plus b by noting that the magnitude of a plus b in this triangle, this is a plus b here, the magnitude is equal to the square root of the magnitude of a squared plus the magnitude of b squared minus 2 times the magnitude of a times the magnitude of b times the cosine of the angle between them, which, you could do that, but that's, again, also a hassle. But it's not particularly convenient. Instead, we can use these things called components. So first, we're going to leverage a few facts. The first fact is that any vector can be broken up or can be decomposed into the sum of more than one vector, right? If I have a vector that looks like this, I can replace that with the vector that goes up by some amount and the vector that goes across by the appropriate amount, right? and then you add them together, and you get the same vector back. So you can always decompose a single vector into a sum of multiple vectors. Similarly, it's very easy to add parallel vectors, because if I have a vector that points in this direction and I add to it another vector that points in this direction, all that is just adding together the magnitudes, right? And the final fact that we're going to leverage is that trigonometry, all this business that we might be involved with, is very, very easy if you are only working with right triangles, right? So what we do when we're working in, say, two-dimensional land is we select two perpendicular axes, and then break up each vector into a sum of vectors pointing along those axes. Sorry, writing this out takes some time, but this is important. So we might say, let's just call these are two parallel axes, maybe call it x and y. So what we do is if we have some vector, say a, we would break it up into a component that goes vertically along that axis and a component that goes horizontally along that axis. And so this this length here, that's what we would call ax. Sorry, ay. This length here is what we would call ax. And how do we get the vector back from ay and ax? Well, there are unit vectors that point in the direction of y and point in the direction of x. We call the vector that points in the direction of x, we call that x hat. Seems kind of intuitive. We call the unit vector that points in the direction of y, y hat. And so how do we get the vector a back from this ax, ay, x hat, and y hat? Well, we just write what we know about how vectors add and how vectors can be multiplied by a scalar. The vector a is just the unit ax the magnitude ax times x hat that produces this longer vector in the x direction, and then we add to it ay times y hat. And that's how we do it, right? So now we can just talk about individual components of those vectors in various directions. And if you have another vector, say, maybe it's bx in the x hat direction and by in the y hat direction, now adding these two things together is much easier, right? Then a plus b vectors is just, well, it's ax in the x hat direction plus ay in the y hat direction plus bx in the x hat direction plus by in the y hat direction. But we're cleverer than this. We can do some algebra and we can group. This is ax plus bx in the x hat direction plus ay plus by in the y hat direction. And now we know what the components of the new vector are without even drawing it out, which, I mean, it seems obvious now, but it's remarkably powerful. Now you might ask, how do we find the magnitude of a plus b, of the vector a plus the vector b? Well, how do we find the magnitude of anything? How do we find the magnitude of, say, a? If we know that it has a base and a height of certain lengths, and they form a right triangle, which of course they do because our unit vectors x hat and y hat are perpendicular, then the magnitude is just the square root of the sum of the squares. So the magnitude of a plus b would just be the square root, this is the Pythagorean theorem, of ax plus bx squared plus ay plus by squared. And this is, so once we have the components for a given vector, in this case, ax plus bx is the x component of the vector a plus b, ay plus by is the y component of the vector a plus b. Once we have the components, all you do is you just square them, add them, and take the square root, and you get the magnitude. So components are remarkably powerful. And they're very, very useful because it gives us a symbolic way that we can actually talk about vectors. Now, it's 2 o'clock, so we're out of time. I will continue with this on Wednesday. We got about as far as I expected, honestly, especially because we had about 20 minutes of preliminary stuff to get over with. I'm going to keep this going for about another 10 minutes just to answer any last minute like administrative questions that there are, but I'm going to stop the recording here. So